Hello, everybody. Now we talk about the differential form, which is very popular form of Maxwell's equation, and the integral form, which has a multiple option to express Maxwell's equations in integral forms. So, in order to understand what the really equation means, you need to understand both sides. Okay, the first one is divergent D equals what? The charge density. Not charge, okay? Charge density. And what does this mean? This is the vector R and divergent to D. D is R minus R. What does this mean? Suppose you are looking at charge. There's some charge at location R, and you look at this location. How much D exists here? Okay. So it's going to be the derivative of D is going to be the Q. This is a strange way to say it, but it's a differential equation. If derivative of D become Q, what is a Q? First of all, this I would say Maxwell's equation differential form we should write this way, because we are talking about what we are talking about. D is electrical field, right? So electrical field is generated by Q. So this equal means the D caused by Q. That's what it means. The Q at the location R, and the point of interest is R prime. Okay, so this is R minus R prime. Okay, how much D exists because of the Q here? That's what equation is claiming. How much D exists? Well, we know derivative divergent D will be the Q. Okay, so this is a differential form, and the Q calls the D, but it's a differential equation form, so we have to solve it. Now suppose you take this sphere and you integrate, right? So you integrate in this sphere. It's going to be total charge Q in the sphere. Then what kind of D you get on the surface, which is volume integral of divergent D is going to be surface integral of this sphere D, and this is a surface vector. Surface vector is, you take a small vector ds pointing outward at the 90 degree. Okay, so the integral form is going to be d ds equals Q. This is Maxwell's equation integral form. Okay, so are they equivalent? Well, they can be equivalent with a condition that you can take any size, any location of sphere. This is called boundary condition. Boundary condition is something you indicate here. Say omega. You take integral on the shape omega. Okay? And this boundary condition is any size, any location. As long as you have this condition, then integral form of Maxwell equation is going to be same as this. And this is Gaussian equation, right? The Gaussian law, and integral form is this one. Okay? So this one, if it's a sphere 4 pi and the spheres A, right, square, and epsilon E becomes Q, so E becomes 4 pi A square epsilon Q. Now this, do you remember that we talk about potential? Potential, this is gradient phi. Phi is a potential, right? So the phi becomes 4 pi A square. Well, in this case, we make A R, so R Q. So this is the potential, and the potential, you can get electrical field. So everything's cool here. Now how about divergent B? Next equation is 0. So nothing caused B. Well, the B doesn't yield nothing, but the nothing can cause B. What does this mean? Okay, the magnetic field can exist in the loop. The loop only is a permanent magnet. Is also existing in the loop. So that's this equation imply the B vector field is always loop. Okay, so you use a Gaussian method to calculate B ds is still 0. Well, actually it could be constant, right, when you take a integral, some kind of value. So it doesn't give you much information about what to do with this B. You don't need anything to generate the B. First of all, B is artificial field, and this one of my previous video shows actually B was artificially created to make a Maxwell's equation symmetric. Not actually, B doesn't really exist. It's Lorentz force caused by B, magnetic field, is actually Coulomb's force, according to special relativity theory. We can explain that. One of video explained that, and if you know that, then B is not really something coulombs, the charge causes a force, just like gravity causes a force. So Einstein said that gravity is not a force either. I mean, it's a skew of the space. So it's it's keep changing. The physics keep changing, but B is not really the Lorentz force. It's just one way to calculate using a differential magnetic field. Actually, the Coulomb, the force. Okay. Now, the next one is H equals J plus this one. And in the previous video, I explained if you ignore this transient area, then it's become Biot-Savart law. They call that law, but it's actually integral form equation for pi you take an integration times dr, right? And that's going to be the B. Okay, so the integral form, one of integral form is Biot-Savart law, and this help you to calculate the meaning of this is when you have a J somewhere in the space, current density, that's cause magnetic field. H somewhere. Okay, again, say this is R, and the point of interest is R prime. So R minus R prime is the location, the distance where the magnetic field is caused by current density. And you take a integral, volume integral, then this become this Biot-Savart equation. Okay, so the volume integral is translated into I. The current density is bundled together, become I. So line was running like that, and take an integral along this line is going to give you exact magnetic field strength. This is I here. Okay, so that's the integral form of the Maxwell's equation. Next one is E. E is caused by what? Change of magnetic field. So if you have a magnetic field here and it's changing by time, okay, then that's cause electrical field at the distance. Again, the location of this change is R, and R prime is a point of interest. The how much electrical field is generated by this magnetic field change. This is R minus R, right? So if you take a integral, in this case we take an integral with this surface, right? Then minus t b ds we have a ds, and this one by Stokes theory it's become e along with this line dr line integral. So this line integral will be the change of magnetic flux in this boundary condition, and this boundary condition again can be anywhere, any size. This equation is valid, and that's the way we can claim either differential form or integral form. So here I want you to think about, suppose you have a conductor circle, right? And this guy calls E. Okay. Say this guy is inside this boundary, right? Because you take a integral ds this area, if outside it's going to be 0, so it's stay inside. Okay, so then cos this E, and E means this is potential, right? So potential is higher here than this, and this one higher here than this, higher here than this. Go circle, come back. They come back to the same potential. What does this mean? Well, if you take from here and go along the sign, its potential goes up and goes up and goes up and goes up. Okay, and this is the potential difference at that delta R. And depend on the material of these conductors, if resistance is R, this potential is called J, the current, right? It's actually I for this wire, and it's generated in this way, and dr gets small, it's going to be continuously going. That means this guy, magnetic field, is going to create a little battery all around circle. Okay, so this guy calls the invisible battery inserted into this ring conductor. So you know how to solve this Kirchhoff's theory, right? E1, E2, E3, E4, and this is R. This is the situation. Okay? So if you take a integral, you have this is become the total voltage generated. The total voltage generated along this line. This is the voltage generated, and you add up all. This is the total voltage generated. Divided I is going to create current. Right? So the change of B causes the current. Okay. So this is the fourth Maxwell's equation, integral format. Now, Um, when you have a current I, you have a B, okay? And when B is not changing, it doesn't do anything. If you give sine wave here on this I current, then B is going to change, right? And generate the electrical field. And if no conductor, it still generate electrical field, because simply resistor R is big. The current is very tiny here, but it's generate. And this is sine wave. This E generate B again, right? And that's generate E again. So if you force a sine wave current on this conductor, single conductor, this conductor generate magnetic field, electric field, magnetic field this way. How far it's go depends on the energy level, right? The distance, and it's propagate. So this is the EM wave, right? Electromagnetic wave, and speed is light speed, c. Okay, so this one of the video shows how to solve this equation, combine last two Maxwell's equations. Then you get the wave equation. You solve that differential equation and it become wave. You get the speed c, and depend on the condition of the atmosphere and the energy level. This goes in 3D all direction, so energy is spread out and becomes thin, right? So this is EM wave generated. So equation imply already that because of this B change cause E, and E cause B again, because E cause I and I cause B again. So it's the initial wave is sine wave, then sine wave propagate all the way in the space. The E is generated regardless you have a conductor or not, because it's just a very high resistance materials. There's some current flow like that, and then that generate another B, so and so. Okay, so that's all the meaning of Maxwell's equation. Okay, I hope you like this video, and if you like, please click like and subscribe, and wait for next video.